Yeah, no worries. Can you see the cursor okay, Sheree?
Yeah, that was good.
Perfect. Yeah, well, thank you very much to, first of all, I'd just like to quickly thank Sheree for hosting this and asking me to give a talk. It's great to present some of this work. So this work is really a hangover of my PhD, a sort of long hangover. So it started off as part of my PhD work and has really grown into its own as I've taken up a research position here at the University of Arizona. So I'm just gonna, and so what I'm going to be talking about today is the cooling history and crustal evolution of Central Asia. So this is the Central Asian edifice. This is the area that I'll be talking about today. Central Asia, it's the largest landmass in the world. It contains a variety of orogenic systems. The largest mountain range, the tallest mountains in the world, are the Himalaya, the world's largest orogenic plateau, colossal intramontane basins like the Tarim, as well as extensive intracontinental mountain ranges like the Tian Shan and the Altai. Besides hosting a range of elevations, this region is the topography and the formation of Central Asia has played a hugely important role on not only the tectonics but also the climate, the biology, and even the society, even human society. And the region itself, here's a bunch of squares where I'm going to show you a series of photos to show the range of topography that can be observed in the Tian Shan, or sorry, in Central Asia. So in the top right-hand corner, we have that's the Kizilkum Desert in western Uzbekistan, flat and dry. Out here is a large high elevation intramontane basin. Intramontane basin of the Dzongkul in Kyrgyzstan. And then we have these really large incised gullies, incised ravines on the margin of the Tibetan Plateau in the Sichuan province. And then we also have the largest topography in the world, the highest mountains, Mount Everest in the Himalaya. So there's a variety of landscapes, really, the variety of landscapes and the land itself has generated progressively over the course of the Phanerozoic due to multiple collision accretion events of various terrains and microcontinents, all sort of building into the current extent of Central Asia. The time period of accretion that I'm interested in, or I'll be looking at today, is the Phanerozoic, and starting at the Permian. So I'm going to just show a series of schematic, geodynamic, artistic interpretations of these collisions, and the top right-hand corner is the Proto-Eurasian margin, with some of the most prominent of these collisions being the closure of the Paleo-Asian Ocean around the Permo-Triassic, the collision of the Changtung block with Eurasia around in the Jurassic, and the collision of other collisions during the Jurassic, and the collision of the Lhasa block during the Cretaceous, all culminating in the collision of India with Eurasia at 60 MA. The schematic diagram had 40 MA, but India is still very south at this point, and my colleagues wouldn't be very happy if India hadn't collided firmly at 60 MA. So we're staying a bit older than that. So these collision events. So then this progressive collision has really generated Central Asia and the landmass that is in Central Asia. But what of the modern topography? Is the modern topography a reflection of these incremental collision events? Do we see these sort of periodic collisions or bits of land that have locked on to Central Asia and reactivated and brought some rocks to surface? Or is the current topography a reflection of that most prominent of those collisions, the India-Asia collision? Have long been explored by a variety of workers all throughout Central Asia, and one of the most applied tools has been thermochronology. Thermochronology is the sort of method I'll be using today, and in particular low temperature thermochronology. Low temperature thermochronology is a form of radiometric dating where, rather than getting like a crystallization age as you would for a zircon, uranium, lead age, what you get a record is a time of which a rock has passed through a certain temperature window. I will be focusing mainly today on apatite fission track, and apatite fission track has a temperature window of 120 to 60 degrees. And this temperature window is quite low, but if you assume a pretty normal crustal geothermal gradient of, say, 30 degrees per kilometer, really what this thermochronometer is telling us is it's telling us the time of which the rock has gone to the upper crust, the time at which that this rock is likely to be exposed at surface. So there are several different ways to bring a rock to surface. One is via tectonic exhumation, like this in this schematic by Ehlers 2005. And in that schematic, they're showing that a normal fault is down dropping, and that's exposing a bunch of isotherms, which are progressively cooling the rock. The other way that we can do it is the other way we can form these, or we bring a rock to surface, is when rock uplift through, say, thrust faulting, rock uplift outstrips the rate of denudation, and so we get the rock being thrust up, that perturbs the isotherm, and then the erosional effects are incising into that block, bringing those rocks to the surface. So here's an example this is a sort of an example from some work by a colleague, Stain Glory, in 2019. And in this range, the Jungari and Altai, I have a series of thermochronological dates, with the oldest being at the highest elevation and the youngest being at the lowest elevation. And so what this is saying is that the rocks first cool to the surface at the oldest time, and then the youngest rocks have just passed through that temperature window. So this is a pretty common approach, and has been done in Central Asia for decades. So those data came from this star out here in eastern Kazakhstan, and I even contributed a slice to this thermochronological question of exhumation. And so I did my PhD on the tectonics of the Western Tian Shan. And so in the Western Tian Shan, what was very interesting is that we found a series of Mesozoic ages preserved at actually quite high elevations, which was interesting in sort of in contrast to this sort of idea of Cenozoic reactivation. And the basis of this study came out of this initial work, where basically I started looking into the thermochronology of the Tian Shan to sort of answer this question of how widespread was this Mesozoic exhumation. In the Tian Shan, there's been a lot of work on this. Some of the original work by Taponnier and Molnar in the 70s, they came to the conclusion that the high topography and massive faults that are in the Tian Shan are a reflection of the India-Asia collision. And so much of the current topography is an expression of Cenozoic collision. Numerous other contemporaries have built on this work. This other one here is a figure by from De Grave et al. In 2007, and they showed that indeed, there was a Cenozoic reactivation along some of these major structures, yet some of the smaller structures within the Tian Shan actually hosted older ages, Cretaceous, Jurassic ages. So it became a little bit more, it wasn't quite as simple as just a bunch of ages, Cenozoic versus Mesozoic. There is this sort of progressive approach. So I sort of started gathering it up, and then I finished my PhD and came and joined Barbara Carappa and her research group here at the University of Arizona. Barbara Carappa and her colleagues focus largely on more southern margin tectonics. So they look a lot at the tectonics of Tibet, the Pamir, and the Himalaya. So they were very encouraging for me to expand my reach out of the Tian Shan, which I was very unhappy to do, and start looking at the thermochron of the Central Asia more holistically. So this is a map of Central Asia, and all of the white circles represent basement apatite fission track ages, published basement fission track ages. There is 2,500 individual ages. 2,000 of those are apatite fission track. 300 of these are apatite helium, and 200 are zircon helium. There are some regions in Tibet, particularly in Tibet, where it's very inaccessible, and there is a paucity of fission track data. And as a result, I used the available apatite helium and zircon helium, but I feel that should be representative because they constrain a fairly similar temperature window. And so this is kind of what it all looks like, sort of a large smattering of color. And it's worth taking a second to sort of do some observations on it, some sort of first order observations. So right here down in the south along the Himalaya and the Pamir, we of course get extremely young ages, sort of 25 to 1 MA, and even younger, even sort of thousands of years are sort of present here on the southern margin. In the interior, in the Tibetan Plateau, we're sort of preserving these older ages of prior collisions. Stepping to the north, the Chilean Shan and the Tian Shan, there is an overwhelming abundance of Mesozoic ages. And these ages get progressively older to the Jamgarian Altai, which preserves the oldest exhumational ages, before stepping over into the Altai Saiyan, which is noticeably Cretaceous, noticeably mid-Cretaceous in age. And I think the observation here straight away is that the Urtish fault here likely represents the end of the influence of that southern margin. And sort of that is, and the Altai Saiyan is being reactivated by processes outside of that southern margin collision. And so with this big data set, we can really get at some very, very simple questions. Namely, how do we reconcile this history of accretion with the thermochronology we observe at the present day? And what is the driving mechanism behind the current topography? Is it tectonics or is it climate? So to do this, I've split the study area into 3 groups. We have the Tian Shan Altai Saiyan, the older ages to the north, then the Pamir Tibet in the center, before finally in the south, the Himalaya. And these data sets I compared these groups to 3 different ways that we can bring a rock to surface, 3 different hypotheses on the exhumation of rocks. The first one being a tectonic influence. So, and to do that, we did a distance from a major boundary. In the case of the Himalaya and Pamir Tibet, I used the India-Asia boundary. And in the case of the Tian Shan and the Altai Saiyan, I used the margin of the Tarim Tian Shan margin, which is the former margin of the Paleo-Asian Ocean. And the next one that we used is crustal thickness. So working in the Western US, there's an idea that that crustal thickness is a necessary precursor to rapid tectonic exhumation. So I used a Bouguer gravity anomaly from Bonnevelotte and some interpretations from Tenzier and Chen to to get at a gravity anomaly data or the crustal thickness. And then finally, there is a lot of work, especially in the Himalaya, relating climate and rivers and rainfall to an increase in exhumation. So here's some work from Van der Beek, and they just show that the stream power, the increasing stream power, is actually leading to sort of younger ages. And to do that, I used a global precipitation model from D and others in 2011. So these are how these maps, this is how it looks in map view. I'm just giving a little bit of an overview before I go into some more detailed scatter plots. The sort of purpley regions represent an area about 80 kilometers thickness. The sort of purpley blue regions about 70 to 50. Light blues 30 to 50 kilometers, before sort of light green being 20 to 25 kilometers in thickness. This is the image of the global precipitation model. Now, each square represents the annual rainfall in millimeters per day. So while limited to look at the current climate, the real power of a global model is it allows us to get a pretty accurate representation on the rainfall for each individual point. And then if we can make this modern day comparison, then we can project it further into the past and make some inferences about the influence of climate on exhumation. In the Tian Shan Altai Sayan, this is the boundary running here along the southern margin. What we see is that there's actually very little, there is a very diffuse relationship between a thermochronological age and distance from the Tian Shan Tarim boundary. It broadly increases in age as we go over that margin, but other than that, there's actually quite a range of ages hosted even quite close to the structure. And again, we see the Altai Sayan really sitting off to the side, not playing around with that southern margin, being influenced by something else. The relationship is really apparent and comes out quite clearly in the Pamir Tibet, where we have the Indian-Asian margin just running along here. And we find that the youngest ages are closest to the boundary, which get progressively older as we step away into the Tibetan Plateau. They're young again along the Kunlun, which is the northern margin of Tibet, before they show this diffuse pattern of aging in the Chilean Shan, quite similar to that of the Tian Shan, invoking the idea that this area has been exhumed for quite some time. And then looking into the Himalaya, everything's really young, but it increases as we're moving away from that India-Asia structure. But what's interesting here is that we get about 100 to 150 kilometers away from this boundary. It's been suggested that an increase in glaciation and rainfall is leading to younger ages, and we do see a decrease in our compiled ages. I took a little cross section, a little swath profile down here in one of my more data dense areas, and basically found that these young ages so here we have the swath profile going from south to north, and the dashed boxes are the extent of major structures that are mapped in Western Nepal. And the young ages relate to this a structure known as the main central thrust. And this is also the area where we expect to experience the most glaciation and the most rainfall. Looking at our crustal thickness in the north, in Tian Shan and the Altai Sayan, we see a positive correlation between thinner crust and older ages. And the way I'm looking at this is that these thin crust areas in the north are more stable and they preserve these older ages, whereas the thicker crustal areas are likely more recently uplifted, as this is a modern gravity anomaly and therefore contains some younger ages. But it's a pretty diffuse model. Any sort of pattern really goes away in the Tibetan Pamir. We We have old ages in the interior at the thickest part of the crust. And then we're actually getting a lot of these young ages in the transition areas between extremely thick crust and just relatively thick crust. So it's sort of suggesting that there's less of that trend here in the gravity and thermochronological age before finally in the Himalaya, where we see, again, no trend. Everything is really young, the crust is really thick. In point sampling with the modern climate, I was actually really surprised by this finding. I didn't expect there to be any relationship at all with rainfall and age. But that being said, there is quite a diffuse pattern where some of these ages get younger with increasing rainfall. At quite low amounts of rainfall per day, sort of 3 to 4 millimeters per year, we're still having this relationship where the younger ages are in areas which experience higher rainfall. The trend really becomes prominent in the Pamir Tibetan region, where the youngest ages experience the highest rainfall, and the old areas are in the driest. The old exhumation ages are in the regions that experience the least amount of precipitation. And in the Himalaya, there was no real trend of rainfall to age. All the ages were young, all the rainfall was high. However, the trend really became prominent when we started comparing it to the Pamir Tibetan region, and that really accentuated that pattern, and possibly even points towards this orographic divide of the Himalaya, really concentrating the rainfall and causing these younger ages. So, just to sort of summarize our range of data sets, in the Tian Shan, with our distance to major structure, Tian Shan Altai, maybe. Pamir Tibet, there is a clear relationship between the age and distance to major structure. And in the Himalaya, we see a clear relationship between the age and the distance to major structure, although the distance isn't very far. In the crustal thickness, there is broadly a relationship in the Tian Shan Altai Sayan, but then this relationship falls down in the Pamir and Tibet, as well as the Himalaya. And then finally, with precipitation, it looks like there is a bit of a trend with precipitation and age in the Tian Shan Altai, and it's very clear in the Pamir Tibet. But then again, in the Himalaya, where a lot of the work's been done, it becomes a bit more diffuse because all the ages are young and all the rainfall is high. So I guess this would point towards the idea that the thermochron and the exhumation ages that we observe in Central Asia are related to major collisional events and the tectonics. So this is a kernel density estimate of the thermochronological ages along the x-axis, and then the number on the y-axis. And I'm just going to start at the north and work my way south. In the Tian Shan, we see the oldest ages relating to some of the older events like the Paleo-Asian Ocean closure and the Changtang collision, as well as the Lhasa, but then a more subdued relationship with that India-Asia collision. In the Pamir Tibet, there's no relationship with the Paleo-Asian Ocean, but then the Changtang and the Lhasa, as well as the India collision, become far more prominent. And of course, in the Himalaya, that's all going to be driven by the India-Asia collision. So I guess this kind of works, but the problem with it, the problem that I see is that there isn't rather a correlation, but like a sort of negative correlation. We're getting these collisional events, and then we're getting this sort of lag time between when we're experiencing these exhumational ages. So is this sort of the collisional events thickening the crust, which they're then being eroded, or is this just sort of simply stresses being transmitted into the interior? Zooming in a bit on the Cenozoic, where we have the majority of our ages, what we can observe is that we've got that India-Asia collision, but then a really notable lag time between the India-Asia collision, and I've been quite broad as a sort of diplomatic gesture to say 45 to 60 MA for India-Asia collision, and then there's this at least a 20 million year lag between that collision and an uptake or an increase in the amount of exhumational ages, which is a bit strange. But then the Tibetan rifting really, really identifies the increase in younger ages at the Tibetan Plateau. But what's interesting is at the end of the Tibetan rifting, the Tibetan Plateau, is also the onset of the Asian monsoon. And that's also where we get an increase in the number of Himalayan ages. So it looks like there is this relationship with climate that just isn't going away. So there's been some really, there's been some excellent work on coupling thermochronology to climate. And this was a study by Oman et al. In 2013, where they took a really large global thermochronology data set. And then they compared that to the global benthic 018 stack, which has been used to prove a cooling climate in the Cenozoic. And they've suggested that the increase in the number of ages in the last 10 million years is related to, is coupled or related or even driven by the cooling climate during that time period. So we have a really good data set for the Cenozoic, and this stack goes over the course of the Cenozoic as well. So I compared how that benthic 018 record looks over the KDE of thermochronological ages. And so we can observe that there is certainly that relationship in the last 10 million years where we have the cooling climate and an increase in thermochronological ages. But it holds up a little less well when we consider the fact that we're getting this increase in our rate of exhumation at a time when the climate's actually kind of warming. And when the climate's showing actually its steepest drop at the start of the Cenozoic, we have no big response of thermochronological age. But the global benthic record is a little misleading. For one, there are very few sample sites in the Indian Ocean. A lot of the data is taken from the Atlantic and Pacific. And the other one is that a benthic 018, the forams that they sample for these records, they sit right at the bottom of the ocean. So they're only going to be perturbed by quite major events. So to interrogate this a little bit further, I got a climate record by Farnsworth et al. 2019. And so what these guys did is they took a series of climate, paleoaltimetry, and precipitation data from East Asia, and they ran it through some pretty complicated, that I'm not that familiar with or comfortable with, simulations in order to get at the Paleo East Asian monsoon, and in particular, the relationship between CO2, precipitation, and the orographic height, or just the past topography. And so what they found in their simulation is that the climate was quite stable during the Cretaceous and early Cenozoic, and then the topography was quite low. And then we see an increase in topography at 60 MA coupled with an increase in the amount of rainfall. If we compare it to the thermochron from Central Asia of the same period, we can pull out there are two big trends to pull out. The first is that we're seeing an increase in cooling ages correlative with an increase in that modeled precipitation of the Paleo East Asian monsoon. Now they've certainly predicted that things should kick off a little earlier, tying it in with that India-Asia collision, and but certainly the increase in rainfall is definitely related, or there is times well with the increase in exhumational ages. And the other observation is that we have a paucity or a lack of thermochronological ages during the Cretaceous Cenozoic, during a period where we're seeing a pretty stable climate, maybe a little bit of flex out here, but realistically a pretty dry climate, and potentially preserving those cooling ages. And so these Cenozoic, the observation of these Cenozoic ages and the observation of sort of Cretaceous, a dry Cretaceous period and not much erosion has also been observed in the Tian Shan. This is a really excellent study by Julian Morin in 2019, and he basically documented a series of planation surfaces across the Tian Shan. And all of these planation surfaces were constrained to be Mesozoic in age. And this suggests that this area has been subaerially exposed for quite a while, at least the Jurassic Cretaceous. And this gives us at least two pieces of key information. The first is that, like with the thermochron, the Tian Shan has actually been uplifted and exposed for a really long time. And the other one is that a dry climate is limiting, that the erosion was quite limited for that period, which relates to those modeled simulations of a very dry climate. So dry climate, pervasiveness of planation surfaces, limited erosion during the Jurassic Cretaceous. So to fold that back into Central Asia and the thermochron and crustal growth of Central Asia, really what we can say first off and sort of dismiss, or not dismiss, but address, is that the crust of Central Asia has been generated in discrete events during the Phanerozoic. It's not all sort of India, Asia reactivating everything. It is this progressive collision accretion events bringing rocks to surface. But now we haven't really addressed the question, and what I'd like to finish with is how that history of accretion does compare to our exhumation of upper crust. And I went in there looking at this thinking that the tectonics would come out to be the most obvious driver, but it seems that the thermochron fits the idea of each collision accretion event, but it doesn't fit it really well. There's this lag behind them. And so to really address this question of does our history of accretion compare to our exhumation, we have to fold in that other question about what is driving the current topography, whether it is it climate, or is it tectonics, or is it climate? And I guess from this work, I've found that I think that, well, the two are inexorably linked. They work in tandem to expose the rock's at surface. The hypothesis here is that we require these tectonic events to generate a thick crustal column. But that thick crustal column isn't really going to do much if there's not processes acting on it. That the thick crustal column uplifts the surface, which then would influence our climate, possibly increasing the amount of rainfall and allowing increased incision and erosion. If we remain in a dry area, like in the center of Tibetan Plateau, or down here, if we're in a thick crust where it is dry in the center of the Tibetan Plateau, we're going to preserve those older ages. But if we're in a thin crust with no tectonic driver, but a lot of rainfall, like in South India, we're going to still preserve very old ages. So from this study, I feel that we've come out of it deciding that from the study, I think we've found that both tectonics and climate are playing a role, where I believe that the tectonics is taking the lead to thicken the crust, and then the climate is increasing those rates of erosion. Thank you for listening. Just before I finish up, I'd just quickly like to thank Marcus Leverström, Kaustub Thirumalai, Pete DeSells, and Paul Kapp for their insights in this project.